All right, I want to go through this question with y'all. So hopefully you can try it first before you watch me do it. So if we have a weak acid, how do we know that it's weak? Well, two reasons. First of all, it's not strong. Second of all, they give me the Ka for it, and it's not a very large number. Like Ka's for strong acids would be like so large, like infinity large, because they go 100% to completion. We want to know the pH. So what's the pH? So what I'm doing right now is just kind of working out for myself. Okay, what do I know from the information given? That's the weak acid. This is the Ka. What is the pH? It's asking me to find the pH. So I know a formula for pH is negative log of H. And remember that H is actually hydronium when it's in water. They give me an amount of the hypochlorous acid. I can just be like, oh, that's probably my initial amount. This H3O plus must be at equilibrium because the reaction is going to move until it gets to that point. We don't want the pH while the reaction's not quite finished getting to its equilibrium point. We want the pH when the reaction gets to its equilibrium point. They don't give me a reaction though. They just tell me, hey, we got weak acid. Well, an acid's not really an acid until it's donated a proton. How does it donate a proton? It's got to have somebody to give it to. So water is what it's going to react with. So we have aqueous hypochlorous acid plus water, which is a liquid, and that is in equilibrium with hydronium ion, which is what water makes when it adds on that hydrogen. And then when we lose that hydrogen, we get hypochlorite. So just think about conjugates, right, when you're doing this. Your products will always be the conjugates. We need to make an ice table because I want to know what is my H3O plus at equilibrium. And right now I only have initial amounts of the acid. I don't even have initial amounts of the products. So I like to make sure that my lines for my ice table are directly under the plus signs and the arrows. They're not exactly straight. That's okay. Cross out your water because the water is liquid. We're not going to be including it. Tell me I have 0.0075 molar of my hypochlorous acid. They did not give me any information about any products. We can just put zeros here. Then for change, we must always be moving toward the zeros because I cannot subtract from nothing when I go to use matter to do chemical reactions. So I must be moving to the right. If I'm moving to the right, that means I'm subtracting the amount of reactants, adding that amount of products. Do a quick check to make sure that my coefficients match for my x's and for my substances. Those are all 1, so that actually works out fine. And then remember that I plus E equals C. So we're just going to add it up. Now I missed a step that I would like you to make sure you always do. If you see K, let's write that equilibrium expression. So we had to write the reactions, maybe that's why I forgot that for a second. But we do need to write our K expression. So K is equal to hydronium, and we can say this is Ka because it's an acid, times hypochlorite over hypochlorous acid. And then we can plug in our E value. So we have X times X over 0.0075 minus X. We need to solve for X because what are we looking for? I want to know the pH. The pH is related to the equilibrium amount of H3O plus, and that is going to be whatever goes in this area here. So I need to know what X is because that's actually going to be equal to my equilibrium amount of H3O plus. All right, and we know this is equal to 4 times 10 to the negative 8 from the information given above. So we could say that's X squared over 0.0075 minus X. Look at that K, it's pretty small. Let's try X is small. So the X is small approximation, or the 5% rule, depending on who you talk to, says that we can just get rid of X in comparison to the initial amount because it's probably very small because the K value is small. So I can just do some quick algebra here. I'm going to rearrange to try to isolate x as best I can. I'm going to pull that 0.0075 over to the side, multiply it by my 4 times 10 to the negative 8 and I get 3 times 10 to the negative 10 is equal to x squared. Take the square root of both sides. Square root of my answer is equal to x is going to be equal to 1.7 times 10 to the negative 5. And now I know that's actually equal to my hydronium concentration. So hydronium is 1.7 times 10 to the negative 5 molar when I want to, if I asked you just for that number to stop. But I need to go one more step. So I need to do pH. So pH is negative log of this number. So I'll do negative log of my answer, 4.76. My answer. Please let me know if you have any questions. But work it out. Make sure that you have the idea of the ice table and then what we do afterwards when we're trying to solve for pH here. And then I want to go over just a couple more things with you. So there are some extra examples. I think I went over that already. But bases do basically the same thing. Bases do basically the same thing. So same generic is going to be B for base, HB plus for the conjugate acid, and then OH minus for the conjugate base for that water there. KB is again going to be your products over your reactants, ignoring the water. And KB is the base ionization constant, or the Ka, but for bases. Here's some common KBs. Do you see something peculiar about this? See how they all have this N hanging out? So if you got something with a nitrogen in it and it's asking you, like, is that an acid or a base? There's a big chance it's probably a base, but these are all neutral, right? Now be careful because if you use ammonium, which is NH4 plus, that thing is a little bit acidic because it's the conjugate acid of this weak base. But basically, for ammonia is one of the really important ones I want you to know. And then anybody that has an amine in the end of its name is based off of ammonia. They have the AM similarity there. And so those are going to be weak bases. So it's the same thing. What's the pH of the ammonia solution at 25 degrees C? So think about it. How would I write the chemical reaction for the ammonia solution? We're literally just going to let it do its own thing in water. So NH3, which is ammonia, plus water, what do we get? And then you do an ice table. And then now think about what you're going to find. Are you going to find the hydronium or are you going to find hydroxide? And then we have to find pH from that, which we talked about in class. So definitely look through the answers if you want to try it. Here's another example. This one is a different type of example. I'd love for you to work this one out. This is asking you, find the Kb of the caffeine. So they tell me what the pH is, and they tell me what the initial amount is. I'm going to give you just a couple little hints here. This is your initial amount. And the pH, we can plug in pH to find, well, you have a reaction here that is hydroxide. So think about how can you connect these two things? How could you connect pH and hydroxide? And the pH will always be whatever it is at equilibrium. So that involves your E part of your ice table. So I want you to think about how you could solve this problem. Maybe we'll do this one in class, or maybe it'll be in a concept check at some point. Work through it and see if you can look at the answers in the next few slides to help get yourself a little bit unstuck. But text me before you look at those answers. So strength of conjugate acids and bases. So conjugate acids are acids. Conjugate bases are bases. But if your conjugate doesn't ever get to go in reverse, it can't act as a base. So for example, HCl, this is an acid, right? So technically Cl minus would be a conjugate base. Can it act as a base? Can Cl ever add this H plus back? No, because it is a one-way street. So chlorine in water is not going to make hydrochloric acid. So the chloride ion is so weak, it doesn't even have basic properties. It's so weak, it's neutral. That ion is neutral. It won't do basic stuff in water. And conversely, if we have, now let's say we have a weak acid. So that was a strong acid. If we have a weak acid, see how we go forward and reverse? So this 8F minus actually gets to go in reverse. And we know this is like 95% of what you got in that beaker. This is only like 5% of what you got in that beaker. So it only ionizes a very small amount, which means the F really doesn't want to let go of the H. So it goes to the left really well. So I don't like they use the word strong. It's not a strong base. It doesn't ionize 100%, but it is stronger. So basically the weaker your acid, the stronger your conjugate base, and vice versa. So here's the strong acid has a weaker, let me just say weaker. A weak acid has a stronger. It's not strong, it is stronger. Weaker, stronger. 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 Weaker. And by weaker, I mean not at all even basic. For like conjugate base, maybe I should just change this. Is conjugate base is not really not really even like a weak conjugate. It's like non-existent. Um, has a weak conjugate, not even. So like it's just like totally neutral. It's not even just like weaker or stronger. Um, Totally never a base. We don't get really even, I don't like even call it, can't really even call it an acid. It's neutral. It doesn't ever get to act as an acid or a base. It never gets to go in reverse. So remember when we talked about K values and how we can manipulate equations and K values, kind of like we did with Hess's law. We can do the same thing with acid-base relationships. This is all just to say this equation right here. So we just know this equation, Ka plus K times Kb is equal to Kw. And that's a good way for us to figure out, well, if I know the Ka, I can figure out what the Kb would be for the conjugate base. So these two things would be conjugate partners. Not just any Ka or any Kb, but specifically if you know the Ka of an acid, the conjugate base would be Kb. If you know the Kb for a base, the conjugate acid would be Ka. So why don't you try to use this formula to answer some of those problems? And we'll pick this back up in class. I just want to give you a little bit of a heads up so that we're more caught up with what we need to be caught up for.